So good morning, everyone. And so today we start with Stefan Hollands' second lecture, and I believe last lecture as well. Yes.
All right, thank you.
Thank you.
So some brief recap. I think I confused quite a few of you with my notation, not intentionally. So let me pretend again we have matrices, and then these are vectors in my Hilbert space, so pure states, and the density matrices. Yeah, and my operators act on this by just acting on the first factor. And my reduced density matrix is just reducing it onto the first guy, so this would be K, I guess, C, I, K. Okay, so this is sort of my notation that I'm using, and my von Neumann algebra then is A, in this case, just the bounded operators on another Hilbert space K. And this other Hilbert space is where these are from. Now, in general, this tensor product is an illusion. It doesn't exist, but it exists under if you okay, and in the commutant, the operators that commute with all operators from here are just acting on the other tensor factor J here. So this is sort of what you usually think. So system A and system B, you have observables in A, observables in B, and they commute, and it's a tensor product. This is not in any way something that's spectacular or should be unknown to you. The general von Neumann algebra case, though there isn't this tensor product, but there is something sort of close to that, which is called the split. And I'm explaining the split at the example of sort of this picture. So you have some wedge W, and then you have some von Neumann algebra A of the right wedge, and so sort of normally we would say the Hilbert space is the tensor product of this and the other side, but that, as I announced, that is an illusion. And then the commutant is just the operators in the other side that you can show. So that's plausible and that you can actually prove. Now there isn't a way to say that somehow you would say that the all operators are sort of the tensor product of these two, and that's just wrong. And if that were the case, you could find a product state. So a product state is sort of a state which is sort of a density matrix times another density matrix. So it has zero correlation function between one and the other. So the correlation function would factorize. So it's just if you have this tensor product, it's obvious how to build this. And such states just don't exist in general. So there are no states in quantum field theory where the correlation functions sort of factorize between left and right wedge. But if you sort of push this inside just by an epsilon, so then you have some pushed inside wedge, then it turns out you can factorize the Hilbert space, and that's called the split. And sort of there's a technical condition, which is the following. So you can consider the boosts in this bigger wedge, and as we've seen, this boost has to do with the modular operator. So this so this is the modular operator for the vacuum. This generates boosts, or the Heisenberg evolution generates boosts of this W. And so then you can consider, let's call this operator algebra B here on the right, and let's call this operator algebra, so B is sort of this. And let's just call this A prime, just to make the notation a bit lighter. And you can consider B from B going into B on the vacuum, and then you take this modular operator for A. So A is, let's draw this here. So this is A primed, this is A, and this is B in a sort of symbolic notation. So you can do this, and A is done this thing here, and you can raise this to the power 1/4. And so now this is in the Hilbert space. And if this mapping is sort of has a, if this mapping has a finite trace, then it is the case that there exists a type 1 factor n, which is sitting in between the two. So it's sitting in between A primed should I do this? A primed. Yeah, it's between A. Sorry, I want to name this A and this A prime. Yeah, so was it sitting between? No, so this way. Had too much steak yesterday, so it's sitting between A and B. So A is this, B is this, and N is sort of fuzzy in between. So N is sort of this. I don't know how to draw it. It's sort of fuzzed out in between these two. And N is the important thing. So in quantum field theory, this is type 3. And this is type 3. And this is type 1. So the importance is that for type 1, you're in this very simple situation with tensor product. So there the tensor product isn't an illusion. And what this is telling you, that if you move this wedge just slightly inside, then you have states that completely decouple this and this moved inside wedge that's coming from this. It's not totally obvious, I think, from what I said, but sort of that's the underlying reason, that you can have a sort of a fuzzed out thing in between, and then in between N and its commutant, you can completely decouple. So that's called a split.
Was it 1/4?
Huh?
What's the 1/4? Where does the 1/4 come from?
Yeah, so if you write it with density matrices, so what this looks sort of a bit mysterious, but if you write it with density matrices, so then if the reduced density matrix for the vacuum is rho, reduced on this wedge, then what this is that B goes into a rho to the 1/4, B rho to the 1/4, and so this rho, morally speaking, is sort of e to the minus the boost generator, and sort of the boost generator is sort of at where the edges meet, so it doesn't damp very well because it doesn't move the intersection, the bifurcation surface. But if you move it slightly inwards, it damps just as well. So this because it's minus exponential, it damps just as well as the usual Hamiltonian. And sort of this provides a very strong damping. You don't have to put 1/4. If you put something else, then it's just the 1/4s are sort of the powers are distributed a bit differently, and it looks a bit asymmetrical. And so, so this sort of trace of this, I'd love to have a path integral formula for this. If you can give me a path integral formula, I would love this. But I don't know. So, but this trace is called the nuclearity index, and it has many properties like a partition function. But unfortunately, its use is very limited by the fact that you don't have a good path. I'm not aware of a path integral formula for it. But sort of from this formula, there should somehow be something like this, because rho to the 1/4 is sort of Euclidean time evolution with boosts. Okay, so now if you have the split, then suddenly you can talk about tensor products. So let me draw this again. And let's now consider, let me look at the following situation. So this is now a time t equal to 0 snapshot of two regions. And let me call now this B and the outside A. And so then you can take the vacuum state. Now I'm using this quantum mechanics notation. And I can reduce this on AB, which is everything. B is this. And or I can sort of reduce it. So let's call this rho AB. And or I can reduce it on A or B. So A slash B. So let's call this rho A slash B. And then I can compute the relative entropy between rho AB and rho A tensor rho B. And I'm allowed now this tensor product because I have introduced a little wiggle room here. And so I don't expect that you follow each and every mathematical detail what I'm telling you now, but I'm saying that this split rigorously justifies this. And now this thing, and let's call this again epsilon here. So this thing now has a chance to be finite. And when epsilon goes to 0, it formally goes to twice the von Neumann entropy of rho A, or B is the same. Yeah, I think you just maybe that's an exercise. Yeah, because then on AB this becomes a pure state. Whereas when you have this corridor C in between, this is not a pure state. So this is this corridor size. But of course we know this doesn't exist. So there has to be really some divergence in this quantity. So this, by the way, is called also the mutual information, this quantity. So there has to be some divergence. And early on in high energy physics, people said that, where this divergence is coming from, you have entangled pairs across here, sort of looking like these dumbbells, many of them. And sort of each correlated pair, counts like a sort of one belt state, sort of one entangled pair. So it creates one unit of entanglement. And clearly, if you shrink this and this becomes very thin, and you self-similarly shrink the dumbbells in the same way, you can put lots and lots of dumbbells around this, and each of them is going to contribute one unit of entanglement entropy. So if you count how many dumbbells you can put, then this is proportional to what's the surface area divided by an appropriate power of epsilon. So really this, you expect that this is the surface area, which is del A, divided by epsilon to the d minus 1.
Can I ask a quick question? Here.
Yes.
You said we need the split to write the tensor product.
Yes.
Can you say again what goes wrong if we don't have the split?
What goes wrong is that this doesn't make any sense because the Hilbert space doesn't factorize. If B is just the complement of A, the Hilbert space doesn't factorize.
Okay, yeah, thank you.
So this is an example of a state which has no correlations between A and B, and I'm telling you that for type 1, there just isn't such a state that has no correlation between the algebra and its commutant. Doesn't exist. And so this is reflected in this divergence. So as far as I know, this argument, this is sometimes called a bit string or something like this. And I don't think people have understood how to make this rigorous, but there is a way to do this, which I want to explain briefly. So rigorous here, it's not that we cannot sleep if no mathematician has shown it's rigorous, but it's because when you analyze these things, you learn some method, and that method sometimes can be useful. Okay, so let's call these regions here A1, B1, A2, and B2, and the way that this works is that you say that S of a row AB so you can show that this is so first of all, you make the system smaller. So you say this is row A1, A2, blah, 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 B1, B2. So these are my dumbbells. And then A1, A2. So this just follows from the data processing inequality. And so you want to somehow say that this is sort of roughly the sum of the entanglement of the mutual information for this plus this plus this plus this. But this is not true because there's also entanglement between these. And so this isn't equal to the sum. But there's a trick that you can lower bound this by another quantity, which is called the distillable entropy. And the distillable entropy is that you take the vacuum state so this is all about the reduced density matrix of the vacuum state, and you reduce it on, A1, A2, B1, B2. So what's the distillable entropy? Or distillable entanglement. So it's one of these entanglement measures that were introduced early on by a guy called Rains in quantum information, and it works like this. So you say, you first pick one sort of dumbbell, A1 and B1. Let's say this one, and so this is the bipartite system. And then, so you can apply to this a set of operations T A1 B1, and this extracts. You extract one qubit, roughly, and you get to so you get a sort of a one qubit state, a bell pair. So you get one bell. So more mathematically, what you do is So this is called a separable operation. So you allow yourself to act with a channel on one of the sides of the dumbbell and another channel on the other, but not something that mixes the two. That's called a separable operation, or a local operation. And you try to find sequences of these local operations. Such that when you apply to n tensor copies of the vacuum state, reduced to A1 and AB1, minus a Bell state on n bits, on n dimensions. So you try to find this that it's zero. So you use it's sort of a trick that people use oftentimes. Instead of dealing with one system, you deal with a large number of copies of n, and then from this you try to distill something. So what this Bell state means is this is just max and this maximally entangled state. So this is on A1, B1. So this means that you distill a large number of qubits from this. So you give yourself 1 million copies of the system, and then from those 1 million copies, you distill as many qubits as you can. So this will not be n, but this will be some number n, which you try to make as large as possible. And then the distillable entropy is the maximum rate which you can get. So it's formally defined as the A1 and B1 for this dumbbell. Is the supremum over all distillation procedures. And then the lim n going to infinity of it. So if you can distill this number of qubits, then the entropy should be log n, as you know, right? But of course, if you give yourself a large number of copies of the system, obviously you can distill any amount of qubits you want. So you have to normalize that by the number of systems that you gave. So it's the number of distillable, log of the number of distillable qubits per copy, yeah? And then this is some optimization over how you distill. Okay, so the pretty thing about this is that this is equal to the sum. This is equal to d A1 B1 plus So while you don't have this additivity for the relative or for the mutual information, because the mutual information not only feels this entanglement, but it also feels that entanglement. And there's no way, I don't think there's an easy way to turn it off. But it's always lower bounded, and that's an old theorem from the Horodecki people. And then this is a property that's not shared by this. And then this gives you one unit of entanglement, this one, and another one, and you just count how many you can have. If you similarly make this smaller, you can put more and more dumbbells, and the number scales just with this. Yeah. And so this just gives a rigorous argument of. So sort of this argument is intuitively used all the time. So here's just a way to how you could argue that.
So, Stefan,
Yeah.
is there an analog, right here, is there an analog of this in, say, like a classical probability system, like
A classical problem, what do you mean?
classical probability, like classical system?
No, entanglement usually you think of as a quantum thing. I mean,
Okay,
yeah. I don't think.
thank you.
Right, so now I want to come to A neck and Q neck. So I think maybe that should be in some people, so, getting into your territory. And obviously I didn't come up with the A neck and the Q neck, but I thought it was totally interesting, and somehow with Brian and others we worked on this, and I want to give you not a derivation of the Q neck as sort of in high energy physics papers, and I don't want to go through that. I assume that this has already been covered in other lectures, but I want to tell you how with these tools, modular theory and so on, you can do something there. And sort of what's the NAC, null energy condition? It's the statement that the stress energy tensor dotted, well, it's classical, that the stress energy tensor dotted with any null vector is bounded from below by 0. Now, because of quantum fluctuations, this is just not true in quantum field theory, where this theta is an operator. But people, a long time ago, have proposed that you should have something like what's called the A neck. So the idea is you take, so I'm just choosing a coordinate system such that u is a affine parameter, that the integral of this is greater than or equal to 0 as an operator. So all diagonal matrix elements are greater than or equal to 0. So this is a strong statement about very many matrix elements. And so let's prove this A neck. How to prove it? So the idea is, and I've seen I've seen this drawing in some of the posters outside, and it's what it means is this. So you take a wedge. Now I'm drawing the edge of the wedge as well. It goes into the board, and another wedge, which is you just move this inside by some angle in quote dependent amount. So if the coordinates along the wedge are ZA, along the edge, then this is this amount by which you move this. Let's call it T of Z. So it varies. So you move it in, and then sort of you have a past light front, and let's call this WT. This. Now then you have operator algebras A for the wedge, the original one, and you have an operator algebra for the wedge which is slightly moved inside. Let's call it A of T. And we have a modular operator for the vacuum, which this is delta. And this is the modular operator delta WT. So if you've forgotten what the modular operator is, so in this sort of tensor product notation, in the tensor product notation, the modular operator, for example, for W is the following. You take the reduced density matrix of the vacuum tensored with the reduced density matrix of the vacuum inverse, where rho W is the trace So sort of these are just formal expressions, but these things exist rigorously, even though the tensor product doesn't make sense. Okay, so this we know what this is. Namely, these are boosts of the wedge. And the crucial property is that if you apply the boost, so we don't really know what these are. Sort of, we think maybe they're angle-dependent boosts. But a crucial property is that any boost will just move this further inside. So a way to say it is that WIT of the wedge, and everything refers to the vacuum, and I'm not going to drop this, of this shifted wedge. Is again going to be in the inside the shifted wedge if you boost in the positive time direction. So you just I think it's clear from the picture. Yeah, is that clear? It's a simple geometric fact. Yeah. Now people sort of in the 90s, in the early 90s, people from operator algebras, they looked at this situation totally abstractly. They said if you have some von Neumann algebras, one inside the other, so obviously A of WT is inside A of W, and if you have such a property that the modular flow of the larger one moves the smaller one inside itself, just like as at rho, then somehow magically you get out a lot of you get what do you mean? You get something interesting out of this, and this were sort of people like Borchers and Wiesbrock and so on. So they didn't at all make the connection with the average null energy condition. They never talked about that, and they didn't see it. But they studied this problem from a somehow totally abstract viewpoint, and their analysis gives something. They give it gives a formula for what happens between this thing. Namely, they show that this is the exponential of I times e to the 2 pi t minus 1 times et, where et, which is really defined by this relation. But et is a positive operator. And furthermore, so ET considered for different T's and the boosts generate a group which is isomorphic to the IX plus B group per generator. So what I mean by this is that this E is sort of a translation, roughly, for on this generator, or let's say on this generator by the amount T, but the T depends on the angle. So it's an angle dependent, it's a translation by an angle dependent amount. And of course you also have the boosts, which is a rescaling on a null generator. So those together give the AX plus B group, A for rescaling, B for translations. But you get a sort of an AX plus B group per generator. And so this is basically, this is very more or less the same as the BMS group. Okay. So that's what this gives, but they didn't see this connection between well, and what's the connection with the ANAC? So morally speaking, then ET is the Z so where I pick coordinates U going this way, V going that way, and ZA going into the board. So it's morally this, and T is a function that's greater than 0, so because I need to move it upwards. And so if I know that this is greater than or equal to 0 for any T that's greater than or equal to 0, then I know that this must be greater than or equal to 0. Yeah, so by the fundamental lemma of the calculus of variations. Yeah, and so so you've proven the ANAC just from this totally general abstract nonsense. Well, so this observation that you can relate it to the ANAC is I've learned from a paper by Horacio Cassini, but maybe it was known to people here as well. Okay. So let's come to the QNAC. Yeah, so as stated, is a statement about wedges in Minkowski space. But because wedges in Minkowski space are so closely analogous to the exterior of Schwarzschild spacetime, you get a quite similar result for horizon generators in Schwarzschild spacetime. You don't get this for an arbitrary null generator in an arbitrary spacetime, because there's no you could define a wedge somehow. You can define a little piece of surface and a wedge, but then you don't know that you have to have as an input that the original, the modular transformation for the original wedge is a boost, and you don't know that in general. And you don't have a vacuum in a general curved spacetime, things like that. But there has to be it has to be true in some sense. It just, I think people, at least I don't know how to really say it rigorously, but there has to be something. Okay, so now what's
Stefan?
the QNAC?
Sorry.
Yes.
Sorry. Yeah. Did you need the fact that you can choose T of Z to be an arbitrary function? Or
Yes, because what you learn is positive is this whole thing, and you need to be able to vary this here to learn something about the integrand.
There's no other trick you could have used to somehow extract that?
No, maybe, but that's how I see it.
Sorry, but this proof actually proves something more general than ANAC, right? This is a Markov property of the vacuum.
Yeah, well, it proves more. I mean, people have said there's more you can say about this setup, but just there's a limitation of time. So this observation is I think, connecting some things that were known just mathematically with some intuitive pictures, and in gravity I found that truly amazing, actually. Okay, so now the QNAC, quantum null energy condition. So people, I guess maybe 6 years ago, they, like Raphael Bousseau and Aaron Wall and others, they had an idea to somehow relate this to something they call the quantum expansion. So I don't want to explain this because it's sort of, I want to give you sort of, my talk is operator algebras and so other people are better at explaining this. But it's a beautiful idea, and it leads to something you can consider a strengthening or of this ANAC. So let's take this and call this, without the integration over the angles, let's call this the ANEC operator. And it depends on the angle. Sort of then there's a more general statement that you can make, which is that for any state, so now I'm taking matrix elements. That this is greater than or equal to minus a variation of the relative entropy computed with this shifted wedge. And omega is the vacuum, and these are always denote the reduced density matrices of any states. I think it may still be. So these are reduced density. Matrix. So for example, this would be the trace over WT. Something like this. So this is not the form in which this was originally given. So this I learned from a paper by Tom Faulkner. He wrote it in this way. And in fact, there's an even stronger statement, which is due to Aaron Wall, I think. And he says that you can even do the following. You can do 2 pi times the minimum over all u unitary in the commutant of this wedge. In the commutant of So this is a unitary in the commutant, which means that the reduced density matrix of the state on the wedge is equal, doesn't change. So this in something in the commutant acts in the opposite wedge. So if you reduce it to one wedge, it doesn't change a thing. But of course, the ANEC operator is an integral over from minus infinity to plus infinity. So it sort of fields both wedges. And the statement is that this is actually equal to this right-hand side. So this is actually equal to minus del. So I think this was called also the and conjecture. Don't ask me why. So this was obtained. Sort of this was conjectures by just in a purely heuristic way, and it's pretty amazing to me that this can be actually proven, and that it leads. It's a quite non-trivial proof that is due to Tom Faulkner and Figret Sayan just a few years ago, or just maybe 2 years ago. So these are sort of difficult, mathematically difficult theorems at the difficulty that just like what these operator algebra people do, and it just follows from these. You just get the idea from these geometric constructions. I think that's truly very very remarkable. But I don't have time to spend on this this proof. I think which would quite benefit from simplification if that's possible. So the relation to this is that of course you can take U to be the identity, and then you obtain something that's bigger, and then you get this. But this is a stronger statement. In fact, if he finds the unitary which minimizes this, this thing, and that's related to all sorts of other interesting questions. So I call this the QNAC, but it maybe if you've seen the QNAC, that's maybe not the form in which you've seen it. You know, people don't use the relative entropy, but they use the actual entropy. But that this is sort of formally implies the QNAC is you can see this. This is explained in these papers. Okay, so I want to come to my last topic. Which is related to the QNAC, but it's not equivalent to the QNAC.
Stefan?
Yes.
A question. So you said strengthening, so the right-hand side is always positive because of DPI, is it?
Yes, that's right. Because
Okay.
if you move this inside, you have access to a smaller set of observables. Therefore, the distinguishability is less. We said that the relative entropy was a measure of distinguishability between two states. And if you have access to fewer instruments to probe the states, then obviously you would think of them as less distinguishable. So that this is a greater than or equal to 0 is obvious, but it doesn't have to be 0. It's just some number.
Yeah, okay. So if I look at the equation the other way around, this ANAC put an upper bound on the difference of the...
Yes, indeed
okay.
it does. Yeah.
Does it mean anything in quantum information?
Well, indeed. So we... probably. I think it's worth... So I think this story is by no means closed. I think that there are more things one can say. So I want to go off in a direction maybe which is similar to what you're asking. So it's about really the difference between the entanglement entropy of a wedge between some state, and I always take the vacuum as the reference, minus S of the shifted wedge. So this is the wedge, and this is the shifted wedge. And so by the DPI, this is data processing inequality, you know that this is greater than or equal to 0, as you pointed out. And sort of this is the derivative of this. So as you take t small and divide by 1 over t, you get this thing. Now, So let me draw the sort of a two-dimensional picture. Maybe this is T, and this is WT, and the whole thing is W. So this is the picture. So in the following, I'll think of this 2D picture, which is sort of just that picture per angle, so to speak, because it's easy. I don't want this 3D picture. And so, as you said, this is sort of this is an infinitesimal version of this difference. And so let's suppose you know that this is very small. Sort of, what can you learn? Sort of, if I restrict myself. So let's suppose this is very small. If I restrict myself to this wedge, you know, obviously. The reduced density matrix here, you've lost some information because you cannot get the full density matrix back. There may have some radiation may have crossed through here, and you've lost this. But if the difference is small, so what you lose in distinguishability is quite small, you should be able to get the reduced density matrix for the full wedge back from the one for the other wedge by approximately. And so sort of in quantum information theory, one speaks of the problem of approximate recovery. So we should so let me write it with reduced density matrices. So So even though I phrased this problem in this very concrete geometric setup of wedges and of quantum field theory and so on, this is actually a very general problem in quantum information. If you have a pair of states and you pass, let's say one you think of as the reference state, the vacuum, but so the other one is the interesting one, and you pass them through a noisy channel, you get a new pair of states, which are less distinguishable, that you know. But suppose the distinguishability only changes by 0.0001. So let's think of an image. You pass through some, through a filter, or you know, across a noisy channel. But just the distinguishability, so the contrast between the image and the empty sheet of paper, you know, that barely changes. Then you sort of more or less know what the original thing was. Yeah? So the general problem is that to say that if you have so the general task, or the idea of state recovery is so that if you have a pair of states or density matrices, so so one is omega c and the other one is omega the vacuum. So this is the empty sheet of paper, or sort of the neutral thing, and now you pass them through a channel. So the channel is in general T. Then let's suppose this is epsilon, let's say 10 to the minus 17 or 10 to the minus 33. So if that's the case, you should be able to find a recovery map. Another channel, so the channel I'm going to call R, such that if you apply R to the thing you pass through the channel, then this should be approximately the original thing. So you get it back. So channels are usually not invertible. They're invertible if they're just unitary evolution. Then you just drive, you know, you drive the inner evolution backwards. So then it's boring. You have it's exactly. But if you have a sort of dissipative situation like here, this is not going to be unitary because stuff leaks out. So you genuinely lose. But the idea is if this is small, which is related to the sort of ANEC expectation value to be small, then you should be able to reconstruct it approximately. So that's the problem.
Sorry, quick question.
Yeah.
So relative entropy is continuous as you shrink the region, but in QNEC you talked about the derivatives. Do we have a physical picture of when does the derivative exist? Like what's are these?
I think the derivative doesn't, it's sort of a left derivative. I think it could jump. I mean, I don't see, you know, because if you have a shock of radiation going through, there's no reason why it couldn't jump.
Yeah.
Just like in statistical mechanics, in the Boltzmann H theorem, if you plot it, it jumps, it can have jumps. So this is like there's an appropriate notion of derivative that's understood here, which is all spelled out in these papers. Okay, so how you would proceed is so this is by the data processing inequality greater than or equal to 0. But if you can put here something that quantifies the overlap between this state and that state, then that would give an upper bound on the that would give you an upper bound or a lower bound on the overlap. And such kind of inequalities have recently been found, and so there is a specific proposal what this recovery channel would be. So in our case, it will depend on the reference state. So we think of the reference state as the vacuum, as some referencing. And this is called the PETS map. It's sort of this, again, in some 1980s stuff. It's not quite the PETS map, but the PETS map is sort of the first step. PETS, sort of, this is 1980 stuff. So the PETS map is 1980 stuff, but the improved inequalities are very new. So what's the PETS map? I should explain to you what's the PETS map. So is that connection between the ANAC and this recovery problem clear, or should I explain it again? So T in this case is the channel which moves the wedge inside the bigger wedge. Yeah. So sort of the partial trace channel over the degrees of freedom that you lose when radiating through. Yes.
Yeah. One thing that's not yet clear to me is from this discussion is, so this recovery is more than just thinking, I mean, taking the T tilde omega state, which has lost some information, and writing it as an operator in this algebra of the larger wedge. You really claim that you can recover some information in a sort of quantum error correction sense?
Yeah, so I'm claiming that so that this thing has, for any psi, this has an overlap. So the overlap between this and this is greater than, this is not so it's greater than 1 minus epsilon. So by overlap, I mean transition amplitude. So you have to define transition amplitude between density matrices, but it's sort of saying that the transition amplitude is nearly 1 for any.
I'm trying to understand the distinction between, or maybe it's not a well-defined distinction, but in the picture where you had like a classical image and you pass it through a filter, maybe a black and white filter, I can still see it's a dog, but I don't know which color of the dog it is. And there's nothing I can do to figure out which color it is. That's just lost.
That's definitely lost.
I can move the picture over to the other side of the filter and it'll still be black and white.
That's right.
And here I think you're doing more than just moving the picture back to the other side of the filter. I think you're claiming that
I'm claiming, so if you've changed the color of the dog and the dog is a cat and sort of then this epsilon would no longer be small. So in this sense you get something on the other side, but it's not really very similar to, you cannot claim that it's similar to that's what you started with. This recovery map doesn't tell you, it's defined so abstract, it's at least not clear to me, what aspect of the state does it recover well, and sort of, clearly you can't recover everything, but you can recover a big amount. So these are quantum states, right? So that you would say they're very similar if the transition amplitude to go from one to the other is basically 1. And that's the kind of statement
what
here.
Confuses
so
me is that
the transition, I don't know what's the transition amplitude between a yellow dog and red dogs probably don't exist, but let's say a beige dog and a black dog was probably very small, and therefore they're not really that similar.
Sure.
And so the
maybe we should
relative entropy this shouldn't be epsilon. So this is probably very large in your example.
I agree that was a bad example,
Yeah.
but we could take a brown dog and a slightly less brown dog after the filter or something. My point is just that I'm confused by the fact that, the state T tilde omega has whatever information it has in it. So unless there's some kind of quantum error correction scheme at work.
Yeah, so the quantum error correction is the R, basically.
Yeah, but what I'm trying to understand is what is the code subspace here? What is the thing that we call the useful information that we're actually after?
In total generality, I'm not able to tell you. I don't know. It's a very good question. I don't know. Maybe someone else knows.
But isn't the recovered state sort of the maximum entropy state that would reduce to that preserves your original, information?
The
Because it sort of, it
maximum
minimizes,
entropy.
it's a Markov, it sort of tries to minimize the CM, conditional mutual information. But, okay, we could talk
Yeah,
about
but I
this
think
later.
what he's asking is sort of, I think in this picture, let's say the state in this contains some gravitational radiation going through the horizon, and then you, after you move the wedge up, you've certainly lost the information of what gravitational radiation went through. But now you recover. What is it? What aspect of this do you recover actually? So I would say that it means that the amount of gravitational radiation had been very small to start with. Otherwise, you couldn't. Clearly, that's lost. You're not going to get it back. But somehow you're processing the gravitational radiation going through at a later time. But it's unclear to me, especially the way this is constructed, what aspect, sort of how this processing works. I think that's your question, isn't it?
Well, maybe a good concrete example to think about is some radiation mode which has very long wavelengths compared to the size of its interval. I think that's a good way to get a small epsilon.
Yeah, that's right.
And maybe there's a sort of best guess for how you would complete that.
Yeah, I think it's an excellent research topic to make this more concrete. But so far, it's just that you have some way to so this R is a channel that does the correction, and there's some formula for this, but I have no idea what it really does. Let's say to a state that you describe, and I think that would be very interesting to figure out. Mm-hmm. Okay, so what's the PETS map? So you can see from the PETS map isn't something that is, to me, something very intuitive, but maybe other people have better, have more intuition. So what's the setup? So you have a channel, T, so it goes from B to A, and sort of T is the dual, the Schrödinger picture of the states. Oh, this is the Heisenberg picture. And then you're fixing a pure state, a state here. On A, I guess. So this is on some Hilbert space. So they call it AA, and this is on some Hilbert space. HB. And then if you have some purification, some pure states here, then T gives you some pure state here. Okay, and now so then you can define something called the KMS Kubo-Martin-Schwinger inner product. I don't know if that's a standard terminology. And what is this? So you take two guys from A. Let's write it differently. So, and it's in density matrix notation. It is so in density matrix notation, it would be the trace of A1 dagger, so that the density matrix, the reduced density matrix here corresponding to this, so omega That's all right. So this is to the 1/2 power a2 with the 1/2 power. So this is what let's just first define an inner product, and you can write this with modular operators to convince yourself that it's well defined. So this is A1 delta modular operator of E and A. And you have the same on B. And so if you have an inner product on some space B and an inner product on some space A, and you have a linear operator between the two, you can define the adjoint. Is that something that sounds okay? Yeah. So in quantum mechanics, there's of course just one inner product, and so you define the adjoint. But if you have two spaces with two inner products, then you can also define the adjoint, and it goes the other way from space B to A. So T, the Pad's adjoint, is you take this adjoint in these two inner products that you have on B. So you can also write this down quite explicitly. But I'm running out of time fast here, so I'm not sure. I may leave this as an exercise for you. Okay, so then there's something called the rotated Pad's map, and I don't think okay, so I'll just define it. I'm working towards this thing here, what this is. So the rotated Pad's map is this. So you you conjugate it with the modular operators, which is how am I going to call it? T, eta, dagger, and T, or something for. So this would be. I'll write down density matrix expressions for this in a minute. Dagger, and then. Minus IT. Then you put something in here, then you have IT. So that's called the rotated paths. So because this is maybe sufficiently unfamiliar to you, I'll write down a concrete example, concrete in quotes. So this is an exercise that you can do. So let's take A to be B tensor with some system C. And inside A you have B. And let's take the channel. So then you have B embedded as B tensor 1. So in other words, T of a B is B tensor 1C. Then what's the dual? So what's this Pad's map? So then you have a state, eta, which gives you a density matrix. Let's call it sigma, is the density matrix associated with this on of eta A, and then sigma B is the density matrix of eta b, which is actually the trace, simply the trace over C of sigma bc in this case. And then what's the Petz map? T, dagger, eta, and little t of some b, of some a, I guess, no, of some b. It is, you take the sigma bc 1/2 plus it t of sigma b 1 minus 1/2 minus it. So I invite you to test your understanding of these definitions by working out this example. Now, what the main result, or one of the main results for this business. Okay, and then there's then let's finally take, so let's take eta to be the vacuum state. Well, let's take define this recovery thing as an integral pi times the integral dt, then 1 over 1 cos 2 pi t plus 1 of this Petz recovery, this rotated Petz recovery thing. So this is my recovery channel, I claim. So this looks a bit complicated. I'll work this out for the case that we're interested in with the wedge just in a minute. But I want to give you first the abstract theorem. Which states that the relative entropy on omega c and omega eta minus the relative entropy after this thing has been passed through the channel T. So if you like, you can just think of these as density matrices. Yeah? Then then this is greater than or equal to minus minus log of the so-called fidelity between r eta t and omega c and omega c. So the fidelity is an analog of the transition amplitude between for mixed states. So you know that if you have two pure states, let's say initial and final, the transition amplitude is given by Born's rule, right? You know that. If you fell asleep, then you should know that. So if you have density matrices, there's a proposal what this should be for density matrices, and that's the so-called fidelity. And for two density matrices, sigma and rho, the fidelity is define as the trace, of the square root of sigma rho and sigma all squared. So it looks a bit bizarre, but if you put in a pure state, you get back this formula. So there's a reason why this is defined, why you say this is considered a good proposal for the transition amplitude. So with this, how you interpret it is that if this is less than epsilon, then a minus log of this is less than epsilon. Therefore, the fidelity is greater than e to the minus epsilon. So it's just about 1 if epsilon is small, just somewhat less than 1. Yeah.
So, from a physical perspective, is it wrong to say that t describes something that's like a boost parameter?
Yeah, so this is just completely abstract, but now when we go to the wedges, then t is the boost parameter. Let me come to this. So this is the general thing. So you could apply this to just matrices, to any kind of channel. And now, of course, we're interested in the situation with the wedges. And let me just give you that.
Well, yeah, I was just going to ask if t is like a boost parameter and you're doing this like integral over boost parameters, is it wrong to say that that's something like saying the Petz map is hard? Like you have to do this integral over.
Oh yeah.
So it's like a complex operation.
Yeah, I think so. Yeah. Very good question. Yeah, I think unfortunately yes. Yeah, it's this stupid fact that you seem to have to integrate over this boost parameter, and I've you can believe me, I've spent quite a bit of time to not have this. I would really like just this original Petz map to be there, honestly, but I have just not been able, and I think nobody has been able to do that. And I've asked the experts in quantum information theory, and they say that they're not sure that, at least with this, with the form that I give here, it's not possible to just do the Petz map. You can just do numerics with 2x2 or 3x3 matrices, and it doesn't work. So unfortunately, you have this a bit complex. I'm not sure I understand complexity, but it's probably complex in a reasonable definition. So let us. So there, another thing that I should point out is that you may wonder why there's a fidelity here. So there are variants of this inequality where you have other information theoretic quantities here. So the point is that it's supposed to measure some proximity between this, and you can find versions of this inequality where you have other information theoretic measures, not the fidelity, but the measured entropy and so on. So there's it's not quite clear that this is sort of the best form of the inequality, but I think it's a very suggestive one. So let's come to this wedge, the wedge situation that we are really interested in. Yeah, so thanks, lots of very good questions. Good research opportunities here, I think. So again, the situation that we are really interested in is this. Yes? Who wanted to? I think it's from 0. Yeah, I think it's from 0 to infinity. Yeah, so yeah. I tried some numerics, just some Mathematica, and it seems you can have situations where you have a contribution, very large t here. Of course, this exponentially decaying function is 1/cos, so it gives a relatively small weight just for the weight factor, but somehow this can be awkward here. Yeah, it's all very good questions. Yeah. Okay, so So we have here so what's the channel here? Channel is the inclusion. So we have the algebra of the smaller wedge inside the algebra of the larger wedge, just sitting inside. And so if we call this T, then the dual channel is the partial trace. If you allow me to temporarily call this part of the system C, so the corridor or whatever, the part of the horizon that you shifted in, then this is just intuitively the partial trace over this, right? And so now, what form does this inequality take? So you can write it in a way like this. 1 over T of S W. And now my reference state is the vacuum. Seems reasonable to do that. And that's anyway what you have in the ANAC. And as you said, of course, in this case, I know in this rotated PETS map we have these modular operators, and I now know they are just boosts, and so I can, they are in principle known to me. And the right-hand side of the lower bound is now minus, and if you work it out, the integral from t to infinity. And let me call the affine parameter u here, and then it's du over u squared. So this comes from the cos, but t here is the boost parameter. So there's a transformation, a coordinate transformation, going from the boost parameter to the affine parameter, and this changes this weight factor to this if you work it out. And then you have the logarithm of the fidelity, and now it's between omega psi, that's the one state, and then you have e to the minus I u p. What's p is the null translation operator in this direction. I p so that's the formula. Actually, this is what the inequality gives you. So it's you take the state. So and this is the fidelity over W. You take the state, and then the overlap is between the sort of translated state. So this is on the state. So the translations on the state goes sort of the other way in the Schrödinger picture. Sort of you push this inside, yeah. And it would be. I think it's an excellent suggestion to take psi to be an excitation of the vacuum containing a long wavelength mode, and try to calculate or get at least a heuristic calculation of what this actually would be like. I think these are all very good research problems. And so I just wanted to state that P is theta u du is the momentum operator. So you have the 1 over t. So this is sort of the difference quotient of what appears in the QNEC, or in the version of the QNEC which involves the relative entropy, which is equivalent to the version originally given. So you may think that you could get the QNEC by just taking now the limit as t goes to 0. But so rather the person who tried very hard was Tom Faulkner, my collaborator on this paper, and Brian Swingle and others, and they didn't succeed. So I'm not exactly sure that this is equivalent to the QNEC, but it's sort of in the same spirit, certainly. And maybe there's a better lower bound such that it becomes equivalent.
Sorry, question?
Mm-hmm.
So is the statement that if this is saturated, then you prove QNEC?
Yeah, so you'd have to show that when t goes to 0, then this sort of becomes an equality, and somehow seems hard to prove that. Maybe not even true.
But if that's true, then it implies.
Then it would imply the QNAC. Yes.
Thank you.
So it implies some sort of a QNAC, but not. Yeah, but I think this inequality, even with t not equal to 0, implies its own intuition of sort of how entropies change, sort of for a fine. And I think that also is interesting to study.
A related question: how much is known about the saturation of the improved data processing? Because that's what we are dealing with here.
Not much. Yeah, I think that not much is known. Okay, but well, maybe sort of one point you can immediately see is that if this was actually 0, so there's no loss of information, so no radiation going through here, then you just know that this is 0, then you know the fidelity is 1, and the fidelity is 1 if and only if they're actually equal. So in this case, this R is perfect recovery, which is sort of intuitively plausible. And that was the case originally studied by Petz, but Petz didn't at all have these more modern inequalities. Okay, I think I'm out of time, I guess, and I think that's a good point to stop here. I think there's still lots to be done. I think it's even the proofs, which are quite complicated, but if you look at them, there are many steps which suggest some interesting things to look at and develop this in different directions. So I think this is not at all a closed subject. Yeah, I guess I'm open to questions. What I'll try is to provide more references to you after the lectures, and maybe if I have time, write up a little summary, because I think that, not many of you know this sort of a bit esoteric approach to quantum field theory, and it's often presented to experts with lots of lingo, which is not useful when you try to learn it. But you have to. If you never receive anything from me, it means I never got. I got. The administrators at my university sort of grabbed me and forced me to do different things when I got home. And thank you.
Thank you.
So you define the PETS map as this, and the twirled PETS map as like this recovery protocol for relative entropy. Mm-hmm. Do you know of an analog for this that uses, say, different measures like the distillable entanglement?
It's just known from what I know. I asked Mark Wilde, a big expert in this, and it's just known for the relative entropy. If you take there's a Renyi version of the relative entropy, you could just put some alphas where there's a log, and then it's not known. Or there's something called the sandwiched. It's not known. The Belavkin-Straszewski is not known. So this seems to be. Maybe it may just not be known. But I've tried quite a bit for these other ones, and I failed. So I suspect that maybe there's known. But I'm not sure.
Okay, good. I think we can go for the coffee break. Thank you very much.